kethone, ketones end in -one, alcohols end in -ol. So chapter 10 is the chapter. We're going to learn a lot of exciting things about alcohol. I always like to say whoever figured out to put this in tobacco needs to be shot. I say about that. All right, here are 3 common alcohols, and we got IUPAC names in green, common names in the normal type. And of course, last semester I tried to drill it into your head, learn your alky groups. So everybody knows ethyl, methyl, isopropyl, butyl, sec-butyl, T-butyl, all that good stuff. So functional groups, alkanes don't have them, but an OH stuck on a carbon is a functional group, as known and understood reactivity chemistry. So that hydroxyl group makes it an alcohol. They are some of the most useful compounds in nature, industry, and around the house. It's just what the book said. We can classify alcohols as primary, secondary, tertiary, or aromatic. We have a whole chapter on aromaticity. So an OH stuck on a benzene ring has a common name called phenyl, and you might have heard of like phenolphthalein, so it gets incorporated into lots of names. All right, what makes an alcohol a primary alcohol? I'll just read these numbers to you as I look off of this slide. Primary alcohol, the OH is bonded to a carbon that's only bonded to one other carbon. Here the OH isn't on a carbon that's bonded to 2 alky groups. That makes it secondary. And here the OH is on a carbon bonded to 3 other alcohol, making it tertiary. So how do we name alcohols? Like always, we find LCCC, the longest continuous carbon chain, but we stipulate we're gotta find the chain that has the OH group, the longest continuous carbon chain that contains the OH group, and we drop the E from the alkane name and add OL. Number the chain, giving the OH group the lowest possible numbers. Number and name all substituents and write them in alphabetical order. It's probably a review. All of you know how to do this a little bit. So once again, primary alcohol, carbon with 1 alpha. Secondary, OH is on a carbon with 2 alpha. Tertiary, 3 alpha. So ethanol, so here the longest carbon chain is 3 for propane, and we have a substituent, carbon number 2, 2-methylpropane-1-ol. Here is a new alky. We have the benzene ring, then we have a carbon, and we name this all as one alky group. It's called the benzyl group. So here we have benzyl alcohol. 4 carbon chain, OH is on number 2 carbon, butane 2-ol, cyclohexanol, cholesterol. Won't make you name that for points ever. Here's our T-butyl alcohol, 2-methylpropane-2-ol. So here's the phenyl and some phenyl derivatives. So we'll have a whole chapter on benzene, and we're going to learn that we'd name this 1,2,3-methylphenol. Here's a common name, hydroquinone. Years ago, you'd buy hydroquinone to develop your film. This is a reducing agent. An OH can get oxidized to a ketone. I'm gonna jump ahead and go all over the map because I'm random. There's the OH, oxidize it. Let me see if alkenols. And you'll recall this from the fall of our keto-enol tautomerization. Raise your hand if you know what that is. Put it down if you totally forgot. That's all right. It's one of the last things with the alkynes. Hydration of an alkyne. All right, so when we have a double bond and a hydroxide, it says the hydroxyl group takes precedence over the double bond. It doesn't exactly say that, I'm paraphrasing. Assign the carbon with the OH the lowest number. So hydroxide has priority over the double bond. Previous to this chapter, you'd start here and number this way to give the double bond the lowest set of numbers. Now you got to give the hydroxide the lower set of numbers. And the old IUPAC, we'd just say 4-pentene-2-ol, meaning the double bond's there. OH is here. The new method, we say pent-4-ol, delineating where all the things are. So my only complaint about Wade is this table needs to show up chapter 1 maybe. Here's the list of your priorities for nomenclature. Carboxylic acids have the highest priority, followed by esters, aldehydes, ketones, and then alcohols. And last semester we started with alkane, got to some alkenes, and got to alkyl halides. So you see an alcohol has priority over double bonds, triple bonds, nitrogen groups, halides. So here, this is the condensed structure. So we have a carbonyl carbon. If we did the Lewis structure, we'd have a double bond going to one oxygen, single bond going to the oxygen that has the OH. So you should recognize this as a carboxylic acid, and the carboxylic acid has priority over the OH, so we number it this way. Eventually we'll have a chapter on carboxylic acids and go over the nomenclature of carboxylic acid. We don't need to know much about it right now. So when the OH is a higher part of a higher priority class of the compound, we call it hydroxyl. So 1, 2, 3, 4 carbon chain butanoic acid from butane. I'll just give you the lesson now. Chop off the E of the alkane and add oic followed by the word acid. So this is known as 4-hydroxyl butanoic acid. Here's an old common name. Alpha, beta, gamma. Had to figure out my Greek letters. Gamma hydroxytritic acid, known as GBH, which is abused by people. It has an illicit drug property. So you can have the sodium or potassium salt, and it can be a powder. And there's this thing called slipping somebody a Mickey, and that's all I'm going to say about that. Alcohol can be named as alky alcohol, like isobutyl alcohol. We generally probably see at the grocery store isopropyl alcohol. So you realize that, I say memorize your alky groups and you get meth, eth, propyl, isopropyl, bute, sec-bute, tert-bute, isobute, and then we forget about it because it gets too complicated. So here's the sec-butyl, isobutyl, IUPAC name, much more straightforward. 1,3,2-methyl propane-ol. I got going on 1,3, so butane-2-ol. Now if we have 2 hydroxyl groups, we call it a diol. 2 numbers are needed to locate the 2 hydroxy groups, and then we use the suffix diol instead of just OL. So 1, 2, 3, 4, 5, 6. We got hexane. We just say hexane 1,6-diol. Don't have to chop off the E when you use the diol. All right, you might have heard of glycolysis, physiological process. 1,2-diols show up in various places, and we use that vicinal. Remember vicinal and geminal halides? So here the hydroxides are on adjacent carbons at diol, known as a glycol. So here's a very common name, ethylene glycol. Used to be put in antifreeze. It's toxic to humans and animals. This is much less toxic. Propylene glycol is really what you buy at the auto parts store nowadays. And here's the IUPAC. Ethane 1,2-diol. 1,3, 1,2,3. Propane 1,2-diol. Phenyl nomenclature. The OH is assumed to be on carbon number 1. For common names of di-substituted phenols, use ortho for 1, meta for 2, and para for 4. And I won't hold you at any of this until we get into the benzene chapter, but we might call this metachlorophenol. For right now, you memorize that this alcohol, phenyl, 1, 3, we got a chlorine, 3 carbons away, so 3-chlorophenol, 4-methylphenol. About does it for nomenclature. Physical properties, at least for 5 semesters, I try and beat intermolecular forces into students' heads, and they all resist me. So one of the strongest intermolecular forces is called hydrogen bonding, and that gives alcohol a relatively high boiling point compared to other things at similar molecular weight. Why similar molecular weight? Every intermolecular force that anything has is London dispersion force, and the greater the molecular weight, the higher the London dispersion force. So big heavy molecules with lots of carbons tend to be liquids or solids. Small things like propane tend to be gases. So here we have ethanol, molar mass of 46, diethyl ether, molecular mass of 46, propane, molecular mass of 44. So the only thing this has going for itself is London dispersion forces, and we see a very low boiling point, minus 42. Now we part this oxygen, this thing's bent, has a dipole, and still kind of a low boiling point, a lot warmer. What did it get to the other day? -8 at my house. Fahrenheit, I have no clue what that is in Celsius. All right, so here's ethanol. Wow, 78 degrees Celsius. You can scald yourself with water that hot due to hydrogen bonding. All right, small alcohols are miscible in water, but solubility decreases as the size of the alkyl group increases. How many of you have heard like dissolves like before? Did I do my job last time? So miscible means soluble in any proportion. You can make 90% methyl alcohol and 10% water, or any variation. I don't think they're really being honest here because I've used 1-propyl alcohol to do an extraction. You can see here something's happening, and as the carbon chain gets longer, it gets more aliphatic. What does aliphatic mean? It means fat-like, and oil and water don't mix. So we have this hydrophobic region here where we have the dipole and the lone pair and the hydrogen bonding. We say this is hydrophilic, likes water, can interact with water. So when we have just a methyl group, all this is powerful enough, does not increase solubility, but as the alcohol's larger carbon chain, we see that here 1-pentyl alcohol, not very soluble. And nobody has to memorize this chart. Wish it had solubilities. Probably the best thing with this chart is to review IUPAC name, common names, practice nomenclature. Now we'll get into some more fun facts. Wood alcohol is methanol. What would be a common name other than wood alcohol? Methanol is IUPAC. And I need quiz questions for Friday. Give 3 names for CH3OH. It's methanol. Here's the new one, wood alcohol. What's the alkyl group with just CH3 bonded to something? Methyl alcohol. There you go. Methyl alcohol, wood alcohol, methanol. All the same thing. Looks like this. Industrial production from synthesis gas. Probably said that a few times last semester. Common industrial solvent, toxic dose, 100 mils. That seems like a lot. I wouldn't want a milligram of this stuff. Used as a fuel. Anybody know much about auto racing? You know, I give out these cards. I didn't give them out to you all because I know you all. And the guy says, I like F1. I'm like, what does that key do on the computer? Because I want to make a joke about it. But I think he meant Formula One racing. I think this might be Formula One. It could be NASCAR. I have no idea. So why is it called wood alcohol? Well, back in the times of alchemists and early investigators, you take like a bunch of wood chips, put them into something like this. This is sealed off from oxygen, and it's called the destructive distillation. And you get things like syngas, synthesis gas. But that's where you get methanol and some other things. Nowadays it's made in a place like Sinclair. High octane rating, low emission, invisible flame. Any questions about methanol? What happens if you drink a lot of methanol but it doesn't kill you? What does it do to you? Makes you go blind. Destroys your retina. Wouldn't be any fun. We'll get that in future. All right, grain alcohol. Why is it called grain alcohol? Fermentation of sugars and starches in grain. So that's a common way to get it. Of course, you can get it from grapes. And wine never gets more than 15% alcohol because at that point, yeast cells can't live, so it kills itself off. Then, of course, distill it. You can get more concentrated ethanol. Last lab we do in lab, we take sugar and yeast, run it through our fractional distillation column, and then the test of how good it is we light it. We pour some on the bench top and light it on fire. Toxic dose. Well, I'm just telling you what the book is telling me. So isopropyl alcohol has the IUPAC name propane-2-ol. Rubbing alcohol. You draw somebody's blood, what do? I give my wife Enbrel shots, and I do the same thing. A cotton ball, some alcohol, and you rub it, and then I put the cotton ball on the nightstand, and it ruins the finish. So that's where the rubbing comes from. And this almost looks like something we studied last semester with acid catalyzed hydration of an alkene. Industrially, it can all be done in the gas phase with a catalyst. That's how it's industrially made. So we can name this isopropyl 2-propanol, propan 2-ol, or isopropyl alcohol. Now we're getting somewhere good with the lecture. Acid-base chemistry, your favorite. I see some grins, so I know it's true. pKa range 15.5 to 18, well, water is 15.8. So in my mind, the acidity of alcohol and water are very similar. And it says acidity decreases as substitution on the alky group increases. Last semester we studied the inductive effect. Halogens and other electrolyte groups increase the acidity, and phenol is 100 million times more acidic than cyclohexanol. And you all could tell me why, because you could pull a proton off, you'd see that it has a charge, and then you could write resonance structures, right? And our magic 2 words, charge delocalization. And I think I got lazy with the slides and I said I'm not going to put one of those slides up. They've seen resonance structures out the wazoo. Here's methanol and water, and for some crazy reason, methanol is just a tiny bit more acidic than water, but the rest follow this trend, excluding putting halogens and things on there. What we said, for the most part, alcohols are pretty close to water, and as you make the chain longer, they become less acidic. Like tert-butyl alcohol, bunch of methyl group, not as acidic as ethanol. All right, now these have that inductive effect. We've studied seeing more acidic electronegative elements through induction, stabilize that negative charge when the proton come off. So here's some common acids, HCl, acetic acid. Acetic acid much more acidic than water, pK of 4.74. If you watch the Zoom lecture that's up for this week from 2 or 3 years ago, I had a fancy demo. Sorry, I didn't have a fancy demo. Maybe I'll bring it in tomorrow, where I take an active metal and put it in water, and what happened? It's fissure. And you can say, oh, I took Gen Chem, that's single replacement. It's also a redox reaction. Sodium here is in its its elemental form, must have an oxidation state of 0. Here it's +1. That's an increase in oxidation. So sodium metal gets oxidized. What gets reduced? Here hydrogen has an oxidation state of +1. Here it's in the elemental forms. It must have an oxidation of 0. All right, so same acidity here, so these protons can come off, react active metal. Here we form sodium ethoxide. So you might say, well, man, this is a strong base, a strong nucleophile. I see possibilities hooking this up with alkyl halides and all that exciting chemistry we learned in the fall. Ethanol reacts with sodium metal to form sodium ethoxide, strong base. You use it for elimination reaction. Maybe more hindered alcohols like propanol, butyl react fast, potassium, sodium. Redox reactions can form some strong bases. Notice an acid-base reaction not used to form the alkoxide, single replace redox. All right, so here's our phenol, and just use some sodium hydroxide that pulls that hydrogen off. It's sodium oxide, water. So here we see the acid-base chemistry, and of course, let's relate gotta have a chalk talk. I decided maybe it should be called a explanation, and you'll recognize this as the 2-naphthol from the extraction lab, and that took this out of the ether layer, the aqueous layer, and so we were able to selectively separate these. And you're going, oh, I remember that lab final question. You wanted to add this first and pull this out. This is not basic enough to pull that off, and that leaves that in the ether layer. Then you add this, you can pull it out. When you add this thing first, this is strong enough it reacts with both of them. You get both these in the aqueous layer, and you haven't affected a separation at all. So a little review of what we did last semester. Any questions, comments, yeah buts? All right. We'll pick up here tomorrow.